Now that we know how to determine what type of intermolecular forces are present, we're going to go through a lot of the physical properties that we could see and try to understand what's going on with these physical properties and predict what type of molecules will have the highest or lowest of these properties. So density is mass and volume, right? So physical property, because if we increase mass, we're also increasing volume. But when we start talking about temperature, if we change the temperature, the density will change. So when we talked about how density would stay the same because of adding mass, we also add volume earlier in the class, I also made sure to say it was always at the same temperature. So what does happen to the volume of these particles as we increase the temperature? So the volume, well, we know that solids are very, very close together, right? The particles are very close together. Liquids are spread out a little bit more, and gases were completely random with lots of space. So what happens to the volume of a liquid as it increases in temperature? The volume is going to get larger, so they're going to have more freedom of motion. So if the denominator is getting larger, the density would go down, become smaller. So become smaller as temperature increases because the volume becomes larger and the particles have more freedom of motion. So why is it that some elements naturally exist as solids, some are liquids, and some are gases? And this is true for compounds as well. And we've been talking about this, just mentioning different ones, especially water. I keep bringing up water, and we'll talk about my love affair with water later. But it's going to be based on the intermolecular forces that are present within these atoms or molecules. So if they have lots of intermolecular forces, they're going to be solids at room temperature. So those with the most intermolecular forces will have the strongest interactions with each other, and they will be solids at room temperature. But if they have the least intermolecular forces, essentially no intermolecular forces, they will be gases at room temperature. So metals tend to be solids at room temperature. We do have one metal, mercury, which is a liquid at room temperature, but for the most part, most of our metals, because they have strong metallic bonds, are going to be solids at room temperature. Metalloids, those are the semi-metals, right, are solids because they have strong covalent bonds. A lot of them have network covalent bonds and different types of covalent bonding that are present. But for the most part, they have relatively strong intramolecular forces that cause them to be solids at room temperature. Now, our lighter nonmetals, those ones especially in group A, which are the noble gases, are gases because they have very weak just London dispersion forces. So just the dispersion forces are at work. But we also have our nitrogen, oxygen, fluorine, chlorine, bromine. Well, bromine actually is a liquid at room temperature, but all of our lighter nonmetals are going to be gases at room temperature. So we'll see those, and we can see that on the color-coded periodic table that we have. Now our heavier nonmetals, bromine is a liquid at room temperature. Also, iodine is a solid at room temperature. But we have soft solids like P4. We've mentioned that it's 4 phosphorus bonded together. S8, we also have Se8, I2. These are going to be solids at room temperature. Some of them are soft solids, but they are still solids at room temperature. And that's due to the amount of intermolecular forces that are present. So in group 1A, we actually see this trend that's a little bit different. So we're going from the bottom of the periodic table to the top. So from row 7 all the way up to row 1 in group 1A. We're actually going to see the melting point and the boiling point increase as you go from the bottom to the top. Now, this is becoming very much lighter, so we would not really expect that to happen, but what happens is that as the ions get larger, so as our ions get larger, I'll try to write this out for you. The distance, what happens? The distance is going to become So the distance between the bonding electrons and the positive nucleus is larger. And that's going to reduce the overall attraction. So it reduces the overall attraction. So we've talked about that before. It's talking about Z effective. So this is what we called Z effective before, and we just talked about that in the previous video. Now in group 7, going from the top to the bottom, we have all London dispersion forces only in this particular row, and as we increase in size, we're going to be increasing the forces. So we will see that the boiling points and melting points increase as they go down. So we do see some opposite that what we would think of trends in group 1, but they're easily described by looking at the trends that we've talked about in the past. Now, liquids are the least understood of all of our states of matter, I said, with the 3 main states of matter. So gases are completely random, solids are ordered, but liquids lie somewhere in the middle. Now, there are 3 terms that come to mind when we talk about liquids. So surface tension, capillary action, and viscosity. So we're going to talk about what those 3 terms are, what they mean, and what happens when we're talking about liquids and how they change for compounds based on the intermolecular forces, and how can you predict whether they will be high or low. Surface tension is up first. Now, if you've ever given blood, you have seen, you go to give blood, they prick your finger, and then it goes up in this capillary tube. So this is called a capillary tube. Also, you used a similar type of tube in lab, in the TLC lab. When you were trying to dot your TLC plates, you put the liquid up into the capillary tube. But also, this is how trees get nutrients, is they have capillary action that starts in their roots and pulls up the liquid and the nutrients in the soil up through the leaves. So it's a very important property. It's a quantitative measure. Quantitative means it has a unit and a label, and it's talking about the elastic force that's at the surface. So we're talking about something that's at the surface of a liquid. It manifests in other ways that we're very familiar with, especially in lab, that formation of a meniscus. Now, we have always seen a meniscus for water that goes like this, or some type of liquids that go like this, but there are also meniscus that can form that go this way. So we're going to talk about those, but we have cohesion and adhesion, which are 2 terms that we should learn before we talk about what the difference is between those 2 meniscuses. Menisci? I'm not sure. All right, so cohesion is the attraction between like molecules. So co means like, so we're attracting like molecules. Adhesion, ad usually means different, is the attraction between unlike molecules. So where we're attracting the glass over attracting the liquid itself is going to result in one type of meniscus, versus we're attracting ourselves over the glass is going to be a second type of meniscus. So looking at this, this is water. Adhesion for water is greater than cohesion. So the water is attracted to the glass greater than it's attracted to itself. So that's why we get the meniscus that goes, that goes this way. Yeah, I'm doing my best. Okay. So in mercury, if you ever have to read a barometer that's on the wall, you might have to actually know what you're doing here and reading a meniscus that's going the other direction. So you can see this meniscus is going this way because cohesion, the attraction to itself, is greater than the mercury's attraction to the glass. So that's where we get the difference between the concave and the convex meniscus. So surface tension is a little different than we would expect, but it really is a quantitative value, so we have to have units and labels that go with it. But the intermolecular forces on the liquid are going to be exerted differently for an internal molecule than they will be on something on the surface. Because a molecule in the center is going to be pulled in all directions towards and attracted to other molecules on all sides of it, but a molecule at the surface is only going to be attracted to molecules that are below them or to their side. So they're going to be pulled in a downward motion. So interior molecules are attracted differently than those at the surface. And sometimes that can result in this tight skin that forms over the top of a liquid. So in order to increase the surface area, molecules have to move up to the surface, and when they do that, they're going to actually have to break some of the bonds with their, not bonds, excuse me, the forces with their neighbors. So they're going to be breaking some of the intermolecular forces with their neighbors. And that's going to require a certain amount of energy. That gives rise to the definition of surface tension. We said it's a quantitative value, so it's how much energy is required to increase the surface area by some unit that's an area. So the units are joules, which is an energy unit, divided by an area, which in this case was meters squared. So that is giving us an amount of energy over an area. So in general, the stronger the intermolecular forces are, the greater the surface tension will be because we have to exert more energy in order to move that molecule to the surface. Water has an extremely high surface tension because it forms multiple hydrogen bonds, which is why the basilisk lizard, if you want to look that up on YouTube, can run on water, as well as water bugs. And if you're really looking for some humor during this quarantine, you should look up liquid mountaineering. And if you decide to try it, please send videos to Professor DeVos. So this is what we've been describing as far as these molecules and what they have to do, what they have to break. So I have an internal molecule here being pulled in all directions towards its neighbor. If this molecule wants to be a surface molecule, it currently has 1, 2, 3, 4, 5, 6 different attractions. If it wants to move to the surface, it's only going to have 1, 2, 3, 4, 5 at the surface. So one of these is going to have to be broken, and that's going to take a certain amount of energy. And that energy, in this case, is going to be in joules per meter squared. We can always change this area unit. It could be centimeters squared, right? Any area unit will work. So the effective surface tension is probably something you've seen, especially when washing your car. You can see the little droplets of water where they beat up and they come next to each other. They attract each other. So surface tension and temperature. As temperature increases, it's going to be easier to break those interactions with their neighbors, so surface tension will decrease. So as temperature goes up, surface tension goes down. It's going to be easier for the molecules to break those bonds with their neighbors. And it's going to be harder for a molecule with a lot of energy to be restrained in the solution. So surfactants can become a problem in our environment because they act on surfaces. Surfactants are things like soaps, okay? Soaps, detergents, anything that emulsifies fats. Oh, here it is right here. They are going to decrease surface tension, and when they do that, they create problems for things that are in the environment. So when you go camping or whatever, or you're putting things, you're washing your car, you got to be careful where you're washing your car. Where is that water draining? Because these surfactants get into our environment and they wreak havoc. In general, I know this is a hard time to say that, people use too much soap. And I'm not saying you shouldn't be using soap, because right now I think I would rather have you err on the side of caution. But using too much soap can be a problem, because then the soap will only attract itself. Again, with that cohesion, it will attract itself rather than attracting the germs that you're trying to get rid of. So you have to be careful. We want to use the right amount. And it's not that, oh, a little bit more or a lot more is going to be better, because that's not always the case. Plus, you want to make sure you do rinse it out of your clothing or your hair and whatnot, because otherwise it starts to build up and create gunk. So make sure you're getting soaps and that they're draining into the right places in the environment, and that you're getting ones that are easily biodegradable. Viscosity is resistance to flow. So this one is going to be tough, because it's going to be opposite of what you think, because we're measuring resistance. Now, your car takes oil, and there's a certain viscosity of that oil. So when you say, oh, my car needs 10W30 or 5W20 oil, you're saying 10 weight, and that 30 means something, and the 5 weight, and the 20 means something. These are telling us their resistance to flow. So it's telling us how well they are going to resist flowing, because when we put things like this in our engine, we need it to protect our engine parts. So the higher viscosity, the greater the resistance to flow. You can see something like this with maybe syrup. Syrup is probably something you've all experienced. If not, you could buy some very cheap and take a look at it. Some people heat their syrup up to put on their breakfast, because it will flow faster when it's warmer, but it will flow slower when it's cold. So we don't tend to refrigerate syrup, because there's no need, and it definitely becomes almost impossible to pour when it's cold. So stronger intermolecular forces produce higher viscosities, and this is going to be straightforward, but why is we're talking about resistance. So we're talking about resistance to flow. So this is a very viscous molecule. We've got 3 OH groups on it. It's going to be very attracted to itself. This is glycerol. We often use this as a lubricant in labs and other places. But those 3 hydrogen bonding sites make it a very thick and a very good lubricant. So glycerol is down here, 1.49 on the viscosity scale. Everything on here, everything else is times 10 to the negative third or times 10 to the negative fourth. So blood, mercury, ethanol, water, those are all very low in the viscosity terms, but we're talking about glycerol being more syrupy type of consistency, more oil type of consistency, and it will do a better job at lubricating things. Here is water at 3 different temperatures, so you can see the viscosity of water changes. These are all times 10 to the negative third, but as the temperature increases, this number is going to go down. So we can see that the viscosity of water is actually the highest at 20 degrees and the lowest at 80. Well, that makes sense. Ice is going to be the hardest to flow, right? Solid water. So the closer we are to freezing, it should be harder to flow. And then here we're getting close to going into the gaseous phase. Viscosity, when we talked about in the last video, if you dropped spaghetti noodles or if you dropped beads, you probably would prefer to pick up the spaghetti noodles, because they're going to interact with their neighbors. So anything that has more opportunity to interact with its neighbors, the shape is going to play a role. It's going to have a higher viscosity, versus something that is small and spherical is going to have a very low viscosity, and it's going to pour very easily. So large or long molecules are going to get entangled, and they're going to pour slowly. I guess in this case, think about dropping it on the ground. It might help. So let's try this. These are the 2 molecules I want you to take a look at. So pause this video and try it, and then come back for the answer. So given that they have the same type of intermolecular forces, so I'm telling you they have the same type of forces, liquids that contain longer molecules have a higher viscosity. So which of these would have the higher viscosity? Well, this one is smaller. This is larger. So greater intermolecular forces, because it has greater polarizability. And thus greater London dispersion forces. So this one would have the higher viscosity, the larger one. It's going to be more difficult to pour. Now, some names of phase changes. A solid to a liquid. You guys know this one. Going from a solid, if we were talking about water, that would be ice, to a liquid, that would be liquid water. What do we call that? Melting. Melting is fine. Fusion is okay too. Going from a liquid to a gas or a vapor. Evaporation or vaporization. This is probably the harder one, going from a solid to a gas. This is when Frosty just disappears in the springtime. He doesn't make us puddle. He goes directly from a solid to a gas. That makes it, and it's called sublimation. So that was a hard one if you got that one, cool. If not, well, work on it. Now, a liquid to a solid. A liquid to a solid. So from liquid water to an ice cube. Freezing. Good. A gas to a liquid. Condensation. And a gas to a solid. This is probably the harder one, probably the hardest one on the page for most people. This is like making dry ice. It's called deposition. So deposition. So you need to know those names and what they mean and what the different form of phase change is that comes along with that. All right, so this is talking about the different things that are going in here. And just for this moment, I'm going to write an equation on here called the Gibbs free energy equation. So delta G is equal to delta H minus T delta S. This is Gibbs free energy, positive and negative is what we're going to be looking for there. Now here, this is enthalpy, and this is entropy. And entropy is the measure of randomness. And this is heat energy. And I think we've talked about a couple of those in class already. So randomness, heat energy, and Gibbs free energy overall. So we want this to be overall negative. It means it will be spontaneous. It means it will eventually happen on its own. It doesn't mean it will be quick. If it's positive, it's non-spontaneous. So if we take a look at what is required here, and we can take a look up at what's happening overall. So this is enthalpy. So this is heat. As heat increases, we're going to see that we go from a solid. We can go from a solid and stop at a liquid. That's called melting. And then go from the liquid to the vapor. That's called vaporization or evaporation. Or we can go directly from a solid to a gas, and that's called sublimation. So that's what happens when we're heating up a substance. Those are the terms. Now, what would happen then? What happens to the particles in that same situation? So if we're going up, the randomness is going to increase as well. So in a solid, the particles are ordered, and entropy is low because an ordered system does not have much randomness. But going up to a gas, it's all disorder, and so it has a lot of randomness. So as we go to the top of this page, randomness increases. As we come down, so as a removal of heat, we can deposit and form from a gas to a solid. We can condense back down. So if we're condensing it, then our entropy is going to be decreasing, and our enthalpy will also be decreasing. And if we go back to freezing, they will also both be decreasing. So we can just take a look at how all of these variables are related in this equation, and just what each term means really at this point. The enthalpy of fusion. So fusion means to melt. So going from a solid to a liquid, how much energy does it take? We have to overcome all of the intermolecular forces to melt it. And then we have the delta H of vaporization. This is going from a liquid to a gas or a vapor. How much energy does it take to break those interactions? Now the heating curve for water, if I go from 0 well, here to here, I look at this, I'm going from negative 25 degrees Celsius to 0. If I wanted to figure out how much energy was involved, I would use an equation like this. Q is equal to mc delta T. Delta T means change in temperature. I do see a change in temperature there, so it would be good. But if I look at this part of the curve, this heating curve here, delta T is 0, which would make this entire value 0 because we can't multiply by 0 and get anything other than 0. So we have to use a different equation at these flat points. So these flat points would be the delta H of whatever's happening. Since it's the melting point, it would be the delta H of fusion times the number of moles of that substance we have would give us Q, which is heat energy. Then, for this part of the curve, we would go back to using the Q is equal to mc delta T because we have a delta T again. And then when we get to the boiling point here, and I know that we've talked about this because we talked about it in lab, and what we're talking about right now, I asked a lot of you if you had a drink and it had ice in it, what temperature would your drink be as long as there was ice in it? And you would tell me that it would be cold until the ice melted, then it would start to warm up your drink. And so here we're at the boiling point. All the energy at this point is going into the phase change of changing this from a liquid to a vapor or a gas. So we would use the delta H of what? Delta H vap, because we're vaporizing it, times the number of moles that we were using to get that Q. And then back at the top, this is why we never heat an empty pan, because the energy does still have to go somewhere. Q is equal to mc delta T. This is where you start to ruin your pan if you heat an empty pan. So we can do that. But you know what? Sometimes we can go directly from this point to this point, but we need to use both the delta H of vaporization and the melting, the delta H of fusion to get there. And that would be, oh, I think I took it out. That would be the delta H of sublimation. So delta H of sublimation times the number of moles that are subliming. So a typical heating curve like this, I might want you to be able to just draw it out real quick, just no temperatures, no values or anything. But where is it a solid? Where is it a liquid? Where is it a gas? Where are the phase changes happening? That kind of thing. So you might want to be able to do that. You should be able to do that with a heating curve like this. You will not need to calculate anything with these values, with the Q's, but you may have to calculate with the delta H's, since you already know how to calculate moles. All right, so let's take a look at these values. For fusion, for melting, ammonia 5.66, delta H of vaporization 23.33. Benzene 9.87, vaporization 30.72. Ethanol 4.93 for fusion, 38.56 for vaporization. Helium 0.02 up to 0.08. Why are these so much higher? I want you to think about that. Pause it if you need to. So what is happening when we break these? And I think, maybe I'll come back to this or not, but I'm not sure. So I'm just going to talk about it. So what's happening when we vaporize versus when we go to fusion? So from a solid to a liquid, which is what we're doing in the fusion, we break some intermolecular forces. But when we go to vaporization from a liquid to a gas, we break all the intermolecular forces. So this one will always be much higher because we have to break all of those forces. Now, vapor pressure is we're talking about partial pressure. This one is actually, I think, the hardest for people to answer correctly because it's opposite of what you think it will be. So when we're talking about things being dangerous or you see things blowing up in movies, it's usually wrong because they have the liquid gasoline blowing up. But it's never really the liquid that's a problem. It's usually the vapor that's a problem. It's the vapor that's above the liquid that's a problem. So something that has a low or a high vapor pressure can be a problem, or actually has a low vapor pressure, but we'll talk about that in just a minute. All right, so here we have a higher temperature on this red curve, and here we have a lower temperature on this blue curve. Now, the blue curve is telling me it's starting at a lower temperature, but it's telling me actually both of these curves, I think is why I'm struggling to say this here. They're telling me where is it going to have enough energy that's needed to escape into the liquid here. So if we start at a higher temperature, more molecules are going to have enough energy to escape. So this orange part here is going to have more molecules in it than if we started at the lower temperature. So only the faster moving molecules are going to have enough energy to release and escape into the liquid form, versus here, this blue curve, they didn't have enough energy because they didn't have enough kinetic energy. Because they were at a lower temperature to begin with, they didn't pick up the energy in order to escape the liquid. So vapor pressure is what is the pressure that's exerted by a vapor on the top of a liquid. So here we have, a beaker, and it's got some liquid in it. Let's see, I think it does. All right, so some liquid in here, but we're talking about the particles that are above the liquid in the gas phase. What pressure are these exerting on this surface of the liquid? So at a higher temperature, the higher the vapor pressure is going to be. The weaker the intermolecular forces are, the higher the vapor pressure will be. So this is the one you really need to practice, because weaker means higher, and that is confusing to most people. Because when we have weaker intermolecular forces, it's going to be easier for those molecules to leave the liquid phase and go into the gas phase, meaning we'll have more particles in the gas phase above the liquid, which create a higher pressure on the liquid surface. So which of these would have the higher vapor pressure? Well, this one is larger, so it has a higher intermolecular forces because they both only have London dispersion forces. So higher intermolecular forces means it's going to have a lower vapor pressure. So which one has the higher vapor pressure would be the one with the weaker intermolecular forces. Okay, which one here? This one has hydrogen bonding. This one does not. So this one would have the weaker intermolecular forces, so it would have the higher vapor pressure. Make sure you pause this to do this. So if you haven't been doing so, pause it and go and do those ones. So this is just showing what the temperature effect is on these molecules. So if we're looking at the same molecule, and we should be getting pretty familiar with these type of curves from the news, but this is diethyl ether starting at negative 100 degrees and coming up. Here, this is 1 atmosphere of pressure. Here we have water at 34 degrees. We start coming up here. 100 degrees is when we start at 1 atmosphere, and 100 degrees is the regular boiling point for water. And then mercury here at 200 degrees, and then we come up to 1 atmosphere. It's 357 is the boiling point of mercury there. But we can see that they increase exponentially with temperature. So as as temperature increases, vapor pressure is going to increase as well, because those particles are going to have more energy and they can escape into the gas phase. So electrostatic forces, just as a reminder, there are two types: intramolecular. Intra means within. These are the bonding forces, and they are within, and they determine chemical properties. Intermolecular, non-bonding forces between molecules, and they determine physical properties. We've gone over that quite a few times, but just as a reminder, we're kind of reviewing at that point. So bonds between atoms are intra. So this bond right here that we're talking about sharing the electrons, that's a bonding force. It's a covalent, it's polar, and it would be an intramolecular. So this would talk about chemical properties. Versus the intermolecular forces are the forces that are attracting these water molecules to each other. So these would be dipole-dipole, LDF, and H bonds, because this is water.